Video help for problem 8.3. We're going to look at an echo, and remember the original spin echo was when we had spins. I just tried to pretend like I'm trying to draw a bunch of spins here, making up the magnetization M, all of these different individual spins. And we have a pi over 2 pulse around, say, the x prime axis, where, clockwise rotation, we move them all into the x prime y prime frame and plane. And so now they're sitting there. This happens instantaneously, and we imagine our clock starting then, t equals 0. And then they start to dephase. Their phase is generally given minus gamma delta bt. Delta b changes for them depending upon where they are. So each spin, sort of think of it having a different delta b, or at least some bunch of spins, different groups of spins having different delta b. So they're different for different spins locations, and that gives dephasing for the different spins. So I want to, remember what happened in the original version of the spin echo. We would have another pi pulse along y. We flip these guys. See, there's some, remember that we're precessing in this direction, and so some of them are precessing faster, some are precessing slower. They spread apart compared to each other, and then we rotate them. Well, actually, it would rotate down because it's supposed to go clockwise. And now the fastest one's behind, the slowest ones are in front, and you wait the same amount of time, and they'll end up becoming parallel to each other again before this dephasing continues again. You get an echo. This time, we're going to actually take the pi over pulse, the pi pulse, to be just along the same axis that we had the pi over 2 pulse. Now, so I'm just imagining those spins from this particular time. And remember then, some of them are behind. Remember, phi is actually our good old polar angle phi. So phi is positive, going backwards in this picture, and negative in this direction. But also remember that we choose phi equals 0 along the y-axis instead of the x-axis. Otherwise, it's the same polar angle phi. And now if I take a pi pulse, I'm going to rotate clockwise around this B1. These spins now are flipped in the back here such that this spin here now has angle pi minus alpha using that phi correction. And this also has phi minus beta for this spin. And so it's pi minus whatever angle it was here. And notice it checks. Here beta is negative. So beta minus, a minus beta is a positive number. And so indeed this, remember, I'm trying to draw this. Remember our angle is defined this way, polar angle. I'm trying to draw this in the x prime y prime frame. From y equals 0, y prime equals 0. And then that's pi minus beta, and beta was negative, so this is a bigger angle. It is bigger than pi. And this other one is pi minus alpha. Alpha was positive. It is smaller. Going to that guy. Just remember all these directions I'm trying to draw are in the x prime y prime frame plane. And so in general, here's what happens. Before we apply the pi pulse, we have dephasing going. We've got this, this instantaneous pi over 2 rotating the spins into the x prime y prime plane. Now they start to dephase, and they dephase according to this and have a different phase depending upon their delta b. Then we apply that pi pulse at tau. And what we now have is pi minus whatever angle it had accumulated right at the end of this period. And then the spins proceed to precess as normally. T minus tau, the clock got started again. And if you now just take this, substitute from here into this, you'll get a formula that you will find that at a particular time t equals what? We call that the echo time. It implies that all the spins have the same phis. What phase is that? The clue to what phase is that the signal is now negative. M points in the opposite direction. That corresponds to the azimuthal angle of everybody going to pi, or 180 degrees. And that has given you the answer.